Moving on to question number 8. The figure shows a system consisting of a ring of outer radius 3r rolling clockwise without slipping on a horizontal surface with angular speed omega, and an inner disk of radius 2r rotating anti-clockwise with angular speed omega by 2. The ring and the disk are separated by frictionless ball bearings. The system is in the xz plane. The point P on the inner disk is at a distance r from the origin, where OP makes an angle of 30 degrees with the horizontal. Then, with respect to the horizontal surface, हमें 4 options दिए गए हैं और हमें पता करना है कि कौन सा option सही है. And mostly the options talk about the linear velocity. So, this figure looks extremely complicated and difficult to understand and solve. So, let's see how the solution goes.
It's a very long question, you see. But however, we are very smart, you see. We'll take a very small route to this question. We are seeing that the figure is very complicated and stuff. But we see that the solution to this problem is very simple. Now, if you see point O, it is moving, the entire disk is moving with omega on the ground. So point O will obviously move with r omega on the ground since there is pure rotation. And in rotation, as we had learned, the velocity of the center of mass is equal to r into omega. However, here we know that the radius of the entire system, the outer ring, is 3r, so it will be 3r into omega. A very simple equation, we can see the center of mass O will be moving with 3r into omega, because the center of mass is obviously moving with the entire ring. Now, coming to the point P. The point P is at a distance of r from the center, and if we see the point P with respect to point O, that disk, if we see the inner disk, let's draw it over here, only the inner disk. This is point O, this is point P, this distance over here is r, this distance. So now, and this is rotating in this direction by omega by 2. Okay, so now if we want to find the velocity of point P with respect to point O, we can simply find out by writing down velocity as r cross omega, right? And here we know that omega is omega by 2 actually, the velocity of rotation, right? Let's take vectors this time, since the options are in vector form. Now we see that this angle over here is 30 degrees. Okay, now this V, the magnitude will be equal to r into omega by 2 in this direction over here. Now I'll move it down and draw a point diagram for only point P, right? So now we know that this velocity in this direction is r omega by 2, the speed. This angle over here is given to be 30 degrees, and similarly we can draw over here point O. This angle is 30 degrees again, this distance is r, and this angle will be 30 degrees over here. Okay, so now what we basically need to do is resolve the speed into the two directions. This is the z direction over here, and this was given to be the x direction. Okay, so now we see that in the z direction the component will be r. Let's write down Vz equal to r into omega by 2 into cos 30 degrees, which will be equal to r omega root 3 by 2. Similarly, we can find out the component in the z direction. Vz will be equal to r omega by 2 into sine 30 with a negative sign, because the component will be in the negative x direction, as we can see over here, right? So the negative sign comes over here. This will be equal to minus r omega by 2, right? Oh, I made a mistake over here. It's Vx, right? So now we know Vx and Vz, but this velocity of point P is with respect to point O. We have Vpo equal to Vx plus Vz. However, we need the velocity of point P with respect to the ground. So velocity of point P with respect to the ground will be given to us by Vpo plus Vo. Obviously we need to find the velocity with respect to the ground, since the point P, the options say the point P has a linear velocity. Obviously it's with respect to the ground, right? Now as we had seen over here the velocity of point O to be 3r omega, we did not mention the direction. Here we can easily see that point O will be moving over here in the right direction, which is in the positive x direction. So this will be 3r omega I cap, right? And over here if we put the symbols, this will be k cap and this will again be I cap. Now writing VPO plus VO over here, we find out VPO will be minus r omega by 2 I cap plus r omega root 3 by 2 k cap plus VO from above we know is 3 r omega I cap. Add these points and we know that VP comes out to be 11 by 4 r omega I cap plus root 3 by 4 r omega k cap, which is option number B. So here we have found out that option B is correct. The point P has a linear velocity of 11 r omega I cap minus root 3 r omega k cap by 4.
So that was question number 8. So let's move on to question number 9. A uniform disk of mass m and radius r is projected horizontally with velocity v0 on a rough horizontal floor so that it starts off with a purely sliding motion at time t is equals to 0. After t0 seconds, it acquires a purely rolling motion as shown in the figure. We need to calculate the velocity of the center of mass of the disk at time t0, and in part B, we need to find the time t0 and the coefficient of friction has been given to us as mu. Also, we need to calculate the work done by the frictional force as a function of time and the total work done by it over a time t, which is much longer than t0. So let's see the solution to this question.
Now here we see that in the initial condition, the body is just sliding with the initial velocity of v0. So since we know that the floor is rough, there will be a frictional force acting onto the body at its bottommost point in the left direction, since the velocity is on the right side. Now this frictional force will be equal to mu mg. Let's write it down. Frictional force F equal to mu mg. This force will be acting on the bottommost point in the left direction.
So in sliding, no rotational motion takes place, right? It's only translation.
Since they have shown that it's purely sliding, there is only a sliding motion and no rotational motion. Therefore, we see that there is no rotational motion. However, now due to the frictional force which exists over there, there will be a torque acting on this body which will cause a rolling motion to start. Now, to reach the rolling motion, we see that the velocity of center of mass will have to be equal to r omega. Over here, we can see that due to the frictional force, there will be a deceleration of the body. Since the initial velocity is v0, we can write the final velocity to be v equal to v0 minus at, where a will be the deceleration of the body and t will be the time at which we are calculating the velocity of the body. Right. Now, to find the acceleration of the body, we simply divide the frictional force by the mass m, since that is the only force acting in the horizontal plane. So the acceleration a will be equal to mu g, which will give us the velocity v at time t as v0 minus mu g t. Now we know an expression for the velocity of this body at a certain time t, unless it has started rolling, because here we see that when the body has started rolling, the frictional force will become 0, as the point of contact of the body with ground is now at rest. So there will be no frictional force. Now, to reach the rolling motion condition, we need to ensure that this v is equal to the radius of the body into the omega, so that the pure rolling condition is met. So here we find out the torque first. The torque applied will be equal to mu mg r. Mu mg is the frictional force, r is the distance of the force from the center of mass. Very simple. Next thing which we need to know is the angular acceleration. As the body moves ahead and torque is continuously applied, the angular acceleration will be there and the angular velocity of the body will keep increasing. So now we know that the moment of inertia of this body will be equal to mr square by 2, since it's a disk, and we know from our basics that the moment of inertia of the disk is mr square by 2. Now we know the torque, we know the moment of inertia. Easy to calculate the alpha, which is the angular acceleration. Alpha will be torque divided by the moment of inertia. This will come out to be 2 mu g by r. We just input the two variable values and we find out the alpha to be 2 mu g r. From alpha we can easily calculate the omega at time t, which will be equal to alpha into t, which will be equal to 2 mu g t by r. Now we know the omega at time t and we know the velocity at time t. To find the time t0 when it starts pure rolling, we just put in the values t0 into these two expressions and equate velocity to r omega. Simple as that, because that is the basic rolling condition which we have learned. So let's do it. Let's put in the time t0 and equate the two conditions. So we'll say that v is now v0 minus mu g t0. This is equal to 2 mu g t0, which is equal to omega into r. Right? So from this we can easily find out the velocity at time t0 to be 2 v0 by 3. Let's write it down as v at t0 equal to 2 v0 by 3. How did I come to this conclusion? From here I found out t0 will be equal to v0 by 3 mu g, and since now I know t0 and I know the expression for v from the top over here, I just put in the value of t0 into that expression to find out v at time t0, which is equal to 2 v0 by 3. This is the part A of the question where you are asked to calculate the velocity of center of mass of the disk at time t0. Now moving on to part B of the problem, where we are asked to find the work done by friction at every time t. So over here, if we try to find out the work done by using the concept of force into displacement, it gets very complicated as the motion of the point of contact is very weird. It's very difficult to compute it and all that problem.
Right.
So we use a very basic concept of energy conservation. We find out the final energy at every moment and we subtract the initial kinetic energy from that entire total energy which we have found out. Right. So now work done by friction will be equal to the final total kinetic energy and the rotational energy of the body, which will be given to us by half into m into v square plus half into I into omega square minus half into m into v naught square. This half mv naught square is the initial kinetic energy of the body, whereas the half mv square plus half I omega square give us the total final energy of the body. So basically now the total energy minus initial energy is the work done by friction, since there is no other external force acting on the body. So all the work done is by the frictional force. Right? So putting in the values from the previous part of the problem, we find out that this work done comes out to half into m into mu g into t into 3 mu g t minus 2 v naught. A simple just substitution of the values from the previous part and solving gives us this relation. However, here we need to realize that the friction will do work only till time reaches the moment t0, as at t0 the rolling condition starts, the point of contact has come to rest with respect to the ground, and so any further work will not be done by the frictional force. Therefore, for any time t greater than t0, the work done is 0. So up to time t0, if we try to find out the work done by friction, we will see that work done by time t0 is given to us by half m mu g t0 into 3 mu g t0 minus 2 v naught. This will be the work done up to time t0, and if we put in the value of t0 into this expression from our previous part, we see that this comes out to be minus m v naught square by 6. Here you can see that the work done by friction is negative, as is generally the case, however not always the case.
Okay. So, after T naught, you said that the work done by friction will be 0.
Right.
I have a doubt. Why is that so?
See, now the body has started to roll. So if this is the ground and this is the body, this point is always at rest with respect to the ground.
In rolling motion.
Right. It's the rolling motion condition.
Okay.
Okay. So now the frictional force acting on this body becomes 0, as there is no motion at this point which the frictional force needs to resist. Right. Frictional force basically the work which frictional does is to resist the motion of the body.
Right.
Now since the point is at rest, there is no resistance, so there is no frictional force. Right. So the work done by frictional force is 0, and thus for any time t greater than t naught, the work done by frictional force remains constant at minus mv naught square by 6.
Okay, right. So that was question number 9. Moving on to question number 10. Two uniform rods A and B of length 0.6 meters each and of masses 0.01 kg and 0.02 kg respectively are rigidly joined end to end. The combination is pivoted at the lighter end P as shown in the figure, such that it can rotate freely about point P in a vertical plane. A small object of mass m is equals to 0.05 kg moving horizontally hits the lower end of the combination and sticks to it. What should be the velocity of the object so that the system could just be raised to the horizontal position? This question is extremely important from JEE point of view.
Right.
So let's see how we go about solving this.
Right. So here we see that this system is pivoted at point P. Right. So in the first place, what we need to do is find out the moment of inertia of this system about point P. For that, we need to add the moment of inertia of part A, part B and the small mass m which is coming in, and find the moment of inertia. Let's start with the moment of inertia of part A with respect to an axis passing through point P and perpendicular to the plane, since this body is free to rotate in the vertical plane.
Right.
So the moment of inertia of part A about point P will simply be equal to mass of part A into L square divided by 3. Right? It's a basic rod with an axis passing through its edge.
Right.
Simple?
Yeah.
Next, we move on to part B. Now over here, we see that we'll have to use parallel axis theorem to find the moment of inertia about the point P. Here, what you could do is, you could find the moment of inertia of part B about an axis through its edge and then move it to point P using this L. However, there's a catch over here. You have made a mistake. You always need to remember that for parallel axis theorem, the initial axis which you use has to pass through its center of mass.
Oh, okay.
Right?
Okay.
So you'll have to take an axis passing through the center of mass and then move it to point P.
Okay.
Right?
Yeah.
So now we find out that moment of inertia of part B is mb into L square by 12, which is its moment of inertia through an axis passing through its center of mass. That plus the parallel axis part, which is mb into 3L by 2 square. 3L by 2, from where did I get? This part L over here plus this part L by 2. Right? So that gives me 3L by 2. Now the small mass which is coming in also gets embedded into this body. Right? So that will also be added into the moment of inertia of this entire body. So that will be, let's write it down as Im, which will be equal to m into 2L square. Right?
Right.
Now if we add Ia plus Ib plus Im, this will give me the moment of inertia of the entire body, which we'll write down as I. Okay. Now putting in all these values and the values of the length and masses given to us, we know the lengths as 0.6 meter each. We know the masses are 0.01 kg, 0.02 kg. We know all the values, so we put them in, we plug them in, and we find out that this I comes out to be 0.09 kg meter square. Okay, so now we know the moment of inertia of this body about point P. Now what we need to do is, the question says that this body will now rise to a horizontal position, right? So over here, if we see that while the body is moving up, there is the gravitational force acting on this body, which will provide some torque, Now, if we go on to integrate that torque and with the displacement and all that stuff, it gets a lot complicated since the direction of torque keeps changing. So what we do here is we use the angular momentum conservation, right? So now we know that the initial condition, the angular momentum of the incoming body with respect to point P will be equal to mv into 2L, right? This is the angular momentum of the incoming body. This should be equal to the final angular momentum just after the collision, which will give us I omega, right? From here we can easily find out omega, which is the omega at which the body starts its rotation at the initial condition, right?
Right.
So from here, if we put in all the values, we get the initial omega to be equal to 2v by 3, right? So this we have found out an initial condition to find out the initial angular velocity of the system. Now to find the height, as I mentioned, we cannot use the torque produced by the gravitational force. So we use the energy conservation method, and if we assume the level to be 0 at the point P level, we have to find the initial potential energy of the system. So the initial potential energy of the system will be given to us by let's draw the body again over here. We have this part, we have this second part, and we have this small mass over here, right? So if this is 0 level, the potential energy of part A will be given by mass of A into minus L by 2 into G, right?
The sign is important, right?
Right, because it's below the zero.
Below the
zero
reference
part,
level.
right? The plus the potential energy of part B, which will be given to us by mb into minus 3L by 2 into G, again, plus the potential energy of the small mass which is getting embedded, which is the mass small m, into minus 2L. This is the initial potential energy. The initial kinetic energy of this entire system will be equal to I half into I into omega square. This is the initial potential energy. This is the initial kinetic energy, right? Now, in the final situation, when the body is becoming properly horizontal, we see that the potential energy is 0 since all the parts of the body are on the 0 potential level, and also since the body is coming to rest, the final kinetic energy is also 0. From here we see that since the final total energy is 0, the initial total energy has to be 0, right? So we find out the total initial potential, we add the initial potential energy and the kinetic energy and equate that total energy to 0. By doing this, we find out that omega comes out to be 4.2 radians per second. Since that was the only unknown in the above two equations, we knew the moment of inertia I, we knew ma, we knew L, we knew mb, we knew small m, we knew the gravity, we knew everything else except for the omega. So by doing the potential energy plus kinetic energy equal to 0, we found out omega equal to 4.2 radians per second. Now since we are asked in the question to find the velocity of the incoming mass, the initial velocity of the incoming mass, we use the condition which we had found out earlier, which was omega equal to 2v by 3. We put in the omega value into this expression to find out the value of v, which comes out to be 6.3 meters per second, which is asked into the question.
Right. So it was quite a lengthy and complicated question. Here, basically, we again used moment of inertia and energy conservation, right? So yeah, that was question number 10.